Okay, here we go. Exam 2 stuff. So exam 2 is also kind of far away, so I want to go through things a bit more in depth. Along with this, I would definitely recommend to look back at the study guide that I gave. It outlines specific questions in the Part A and in your homework, and in the recitation that I definitely think that you should go back and look at. So please give that a look-see before asking me like what questions did you look at, and then if you're like that's good but I need more, then come to me, okay? All right, so one of the things that we went over was activation energy and catalysis. Now, this is something that a lot of people had trouble with because they were like, okay, Victoria, but how do I relate this to temperature? And how do I relate this to the catalyst? And what does a catalyst do? And remember that catalysts are the things that lower the activation energy. And activation energy is inversely or directly related to the temperature, in that if you have particles moving faster, then they are going to have more energy to overcome the activation energy barrier. Another thing that I want to highlight is when you're looking at a graph, which relates the rate constant to the temperature and to the activation energy, that you look at the whole equation and remember that you are looking at 1 over the temperature, because a lot of people mess that up when they're going through these types of problems, as well that the slope is equal to the activation energy divided by the gas constant, and as well knowing that when you are using Kp, so when you're working in pressures, that R actually is in bar, and that's why instead of joules per mole it's in bar, and that means it's going to be 0.0821 instead of 8.314. So be sure to pay attention to the units that you're using and the actual phases that your reactants and products are in. Okay, so activation energy and catalysis, kind of similar questions come up, but this is the one that a lot of people struggled with, and that's basically when we have something that says an equilibrium and then something that goes straight forward through, and we're working on finding the actual overall rate law expression. So this is the one that you guys most struggled with last time we talked about these things, so I wanted to go over those ones again, especially because these are ones in the exam that also people struggle with finding the true rate constant. It's the one that I don't know if you remember, but it has K obs. And so the first thing we look at is we know that the slowest step is the one that determines the rate, right? That's straightforward. But the problem is that when I write that out, so that's this one here, is that we note that this is an intermediate. And intermediates cannot be in the rate law expression. And so that means that we have to find how this relates to the actual problem. And so what I have to do is I rearrange this, and luckily this is an equilibrium, which means it's going to have a forward rate and a reverse rate. And I find how NaOCl relates to the other products and reactants. And so I write that equation out with the forward reaction up top and the reverse reaction on bottom, because the reverse reaction has the concentration in it. So if I divide these over, oh my gosh, there's my roommate. She was staring at me through the window and I got really scared. I was like, who's looking at me? Sorry. I divide this over to the other side because a lot of people forget that with rate constant, sorry, it still scared me, with rate reactions, that these can be equal to each other. So I can set these equal to each other because the rates are equal, just one is forward and one is reverse. So I divide this over to get how the concentration relates to the forward and reverse rates, and then I can take this whole expression here and plug it right back into here. Perfect. And that's how I get this huge equation here, and then I get K obs, multiplied by ClO. There we go. So that's because I forgot to carry this over. So there we go. We carry this over to the other side, and that's how we get the full concentration. Now remember that K2 times K1 divided by K to the negative 1 overall is going to say K obs. And the reason for that is because in the exam, if they showed you K times K1 divided by the reverse, then it would be very obvious what you kind of need to do. So a lot of people are like, why do they do K obs and not just show it how they would normally? I'm like, that's because it hints at the answer. So that's why that is the way it is. All right, again, catalysis is the same idea. We're looking for something, except in this one, we notice that the intermediate is also, the intermediate is what we're trying to replace, and we're not looking at the catalyst, which in this case is ozone. So ozone's a catalyst, and it's going to be speeding up the reaction rate overall, which is why this is fast. However, it does not show up in the products because it gets decomposed. And what we have here, though, is we're looking at the intermediate and how that is replaced. So first we have the fast reaction here, and I noticed that the overall reaction is the ozone plus oxygen is to 2 dioxygens. And then again, as I noted, ClO is the intermediate. Now I have the two rates for the fast and the slow reaction. And again, the slow reaction is what determines the rate. But I note that, again, ClO is an intermediate, and so that needs to be replaced. So the formation of ClO is literally the forward reaction of K1, which equals ozone times chloride. So the way that this differs from the previous one is that this isn't equilibrium. And that means that we can't show the reverse, right? It can only go forward one way. And luckily, what it's asking, the intermediate, is a product. And so that means that we have it equal the rate times the two reactants to make ClO. And that's when we can then take this rate and plug this into Cl, because that is what the concentration equals. And then we get, of course, K obs, because this is K1 times K2, times the ozone times chloride, because again, that is what this rate is, and then times the oxygen, because that's from the actual slow step. Awesome. All right, take a breather. Pause the video for those. And then we're going to go into equilibrium, so ice tables. A lot of you guys were like, Victoria, ice tables, what do I do? How does this work? And a lot of people forget these, and I think that that's why they're a bit of a struggle on the exam. So we're going to go through a couple examples of different things. The one thing that I want you to remember is that you want to look how has more moles initially, so at the start. So when it says initial concentrations, and if it's the reactant, then they're going to be minus, and if it's the products, then they're going to be minus. Whoever has more is going to be minus, unless there is, of course, Lechat's principle being applied in that we're increasing the moles of one side. And if we increase the moles of one side, it's kind of like a teeter-totter, and wherever it rolls, think of a ball in the center. And if you increase one side, then the ball is going to roll to this side, right? So that's why this creates this sort of switch in the preference for either side, right? Again, remember to bring down your coefficients. Just because it's 2x, you also have to then square that 2x. That's something a lot of people forget to do. And if it asks you to find k, and it's given at least one equilibrium concentration, then it's in order to solve for x. And if it gives you the concentrations, then you need to use the quadratic formula, right? All right. Okay. So first things first, what I'm looking at here. The one thing I like to note first is always write this down. It helps keep your mind straight in that if K is greater than the reaction quotient, then that means it's going to shift towards the products. And if the equilibrium constant is less than reaction quotient, then it's going to shift towards the reactants. So make sure to kind of keep those things in your mind as you're going. All right, I see that I have 10-liter volume. I know that I'm mixing 1 mole of nitrogen, 1 mole of hydrogen, and then 0.5 moles of oxygen. And I want to know what the concentration at equilibrium is for the nitrogen hydrogen from the reaction. So this is the reaction here. And I know that it says if the equilibrium constant equals 1,000,000. Okay, so I know the initial concentrations of these are going to be the moles divided by liters. So I multiply those all through to get the actual concentrations. And then I'm going to plug those into my initial concentrations. And I know that I have 0 nitrogen, hydrogen, and I have 0 water, because those are being formed at this present and they are not given to me initially. And that means that we're going to be plus the products and subtract the reactants, because I have reactants, so this is already shifting towards the products. So then I know my change is minus, again -4, I bring down that coefficient, and again +2, so then I write down my equilibrium. Now remember, like I said before, if they give you the concentrations and they give you the equilibrium, then you're normally going to be solving for x, and you're using the quadratic, which is what we're doing here. So I set up my quadratic equation, I do the math, and I find out that x equals 0.0237. Now, what we have to know is that nitrogen hydrogen is x, and therefore it just simply equals units. At me, how could I forget that? As 0.0237. If I were asking about water, then I would need to multiply this by 2. If it were asking about oxygen, I'd have to take 0.05, subtract 0.02, etc., and so on. So you'd have to go through all of these steps and make sure that you do get concentrations. Now, somebody asked me, okay, what if, these didn't add up? They do, but they said, what happens? Then I would double check. If 0.01 minus 4 times 0.02, which in this case would be 0.8 something, I would go back through and be like, okay, there is a math error, and I need to go back and check this. All right, Chatler's principle. I wanted to put everything on here and just sort of go through what changes in concentration. It says pressure or temperature. This is because remember that concentration and pressure, Kc and Kp, those are for 2 separate systems. So in this case, we'd be looking at Kp because these are all gases. But if these were, say, aqueous, then we'd be looking at concentration. So changes in concentration and changes in pressure also come to the same thing, but temperature can be a fickle thing because when we take into account exothermic and endothermic, which I'm going to discuss in a minute, is important. So this is asking me to find what's going on here. So we've been given the concentrations of this at equilibrium, so we simply plug that in, and I'm going to find the equilibrium constant. Wonderful. Now we're going to shift this because I'm going to increase the concentration by 3.65 molar, and then I find that this is a disturbance in that system. So when I'm adding something, I'm disturbing the system. And note that it's NH3, and so that is this side. And when I increase this side, this shifts back this way. And now I'm shifted. And remember, when K, and sorry, I'm going to rewrite this, is this way, this indicates a shift towards reactants, right? So this is all following kind of that same thing that we would expect. I know it says shift to the left because that's how it's written in the book, but again, like I said, I like to write them with K first because then the less than or greater than sign points towards the side that it's actually going to, the arrow points towards where it's going to go as well. All right, and so then of course I plug in my new concentrations and I get my new Q, and again, like we could predict from before, our Q is less than, our Q is greater than K, and therefore it's shifting towards reactants. So this again is how I do a quick common sense check, and that's why I kind of wanted to introduce this problem, because you can actually check if you're right or wrong simply by reading out the problem and saying to yourself, what did I expect to happen? Here, I had an increase in products, and therefore I expect then for this reaction to shift back towards reactants, and if it's shifting towards the reactants, then I expect K to be less than Q. The same thing can be said if, say, we increased nitrogen. So say I increased nitrogen and there was a shift towards the products. Then I would say, before even doing any calculations, that I would expect my answer for Q to be less than K. Why do I say Q is less than K? Because again, I increase the products and therefore there's the reactants, and there's a shift towards the products. So it just depends on kind of finding that common ground where you're like, okay, but this is what I would expect to happen. And it's sort of a nice way to double check your answers when you're going through the not only the exam when you get towards those, what are they called? Like theory questions where it does ask you like if K is less than Q, what do you expect? But also when you're doing the actual calculation. So you can definitely double check yourself. And I'm not going to read through this because you guys can read as I've always said, but this is something that I wanted to put on there that's from the study guide that is a very good helpful note to kind of give you an idea when you come across things that are disturbing Le Chat's principle. All right, another thing from ice tables, and this is when simply we are given things, because I think what happens with these ones and why this is most missed is because it's so straightforward that we kind of forget what's going on, and that can be an issue. So this is where that kind of one where it gives you X and then we're going to solve for the equilibrium constant. So again, it says in this reaction the initial concentrations of nitro oxide and nitrogen dioxide was at 0. So we have a starting product, right? And we have no initial reactant. So again, we're kind of going to see a shift this way. And this one I wanted to show because for once the product is negative. Because a lot of the time we're very used to the product being plus. So I wanted to show a good example where it's actually minus. And that's when we are given an initial concentration of products. So there's going to be a shift towards the reactants. So I have 0 plus 2x. And then I have overall 0.09 because that was told to me that that is what was going to be at equilibrium. So I can just plug that straight in. And this means that then I can find out that because of this, I know that 0.1 minus 9 or 0.009 is going to equal this many moles. And this is going to be my concentration here. And we can now calculate this because I know that that is going to be my X value. So then I can use this to find NO2, so I just plug in my X value, and now I have my two concentrations that I need. Again, a lot of people mistakenly plug this in for N2O4. Just please remember that this is the concentration that was at equilibrium. I think that's another place where people go wrong with this question. So please be aware of what you're plugging in. And this, oh, excuse me, my voice cracked. And that's embarrassing. And this is my concentration of nitrogen dioxide. Again, please remember that not only is it 2x, but it's also raised to this power of 2. So be sure to plug everything in as is, and this is what you should get for your K value. All right, and finally, changes in temperature. Just remember in total, I like to remember that exothermic means that heat is a product, And the endothermic means that heat would be a reactant. And this means that when we talk about increasing heat, whenever they're talking about an exothermic or an endothermic reaction, that they are talking about increasing this side. And that means that you're getting a shift towards this end. So whenever they're mentioning, okay, tell me how you expect this problem to go forward if I increase the heat of this exothermic reaction, well, then you'd say, oh, it's going to shift towards the reactants. And then it's going to ask you, well, how would you decrease the concentration of iron? And you're going to say, oh, well, I increase the heat. I increase the temperature. That's definitely how I would do it. These are things that need to take into consideration. Or I would increase the aluminum. Another thing is that they would say, oh, how do I increase aluminum? Well, I decrease the heat because that would cause a shift towards this side. So somewhat being aware of what the language means and remembering that exothermic is something that measures heat because it's enthalpy. Enthalpy is a change in the heat energy of that reaction. Deep breath. Here we go. Acids and bases. The one thing I want to say is please know the definitions of acids and bases. I've said Bronsted-Lowry because these are the ones that people always confuse, and that's going to be so like Lewis acids and bases is like who's the donor, who's the acceptor. Bronsted-Lowry is who's the proton donor, who's the proton acceptor, and Arrhenius is all about hydrogens and all about the hydroxyl groups. So just kind of remember to keep those definitions handy for when you are taking the exam and double check that they're correct before the exam, because the last thing you want to do is doubt yourself during the exam because you have no time to look up definitions when you're wanting to double check your math on top of all that. Another thing to do is I remember that strong acids and bases dissociate completely. Now, I'm going to bring that up more in the next video when we're doing acid-base equilibria, but I just wanted to bring it up here because we do get a bit into acid and bases, and I wanted you to know that it is going to be touched, so don't worry. And then also, remember these equations. Write them down. They will be given, but also I want you to write them down just so you have them at the ready for when you see acid bases, you quickly just flip, and they're in front of you, okay? Just remembering, again, that POH is inverse to the concentration of OH, just as the concentration of H plus is inverse to pH. So just remember that they're inverse, and that's what that negative log is doing to this. And then that we raise these to the power of 10 to the power of pH to give us the concentration of our hydrogens back. All right, so this is a multiple choice question, and in the part A, it gives you a base. And so I wanted to show you what it would be like with an acid, just in case you were curious. And so it's saying that we are adding an acid to water, and it's not changing the volume. So when it's not changing the volume, that means it's definitely affecting pH. Because remember, if we're pH and pOH are technically concentration measurements, but in a log scale. And so that means that if the volume changes, then technically the concentration of H plus is also changing, but it's not necessarily going one way or another because it's actually also becoming dilute, so you don't know if it's actually becoming acidic or if it's becoming just more neutral. But in this case, since it says it's not changing specifically, then that means the concentration of H plus is changing. And then we find out what does this describe when we're talking about hydrogen, OH minus pH, etc. So when I add an acid to water, I automatically think the pH must be getting lower. And I also think if the pH is getting lower, then that must mean that the hydrogen concentration is getting greater. And so I can already look through here and say, okay, pH is decreasing. So that's actually already narrowed it down for me considerably because I know that pH is going down. I also know that means the concentration of H plus is increasing. So just by that alone, I've already somewhat narrowed it down, but I want to make sure that everything else makes sense. If pH decreases, and this means pOH increases, which is very true. Also, if pOH increases, then that means the concentration of OH minus decreases. So this is the question that makes the most sense. It wouldn't make sense that that the OH or the H plus concentration would decrease because I'm adding more acid, and more acid dissociating becomes H plus and NO3 minus, right? So I'm adding H plus to this concentration stuff. So that should definitely be increasing. All right. Another thing. So according to Bronsted-Lowry theory, which species are considered bases and which ones are considered, and of course by that, which ones are considered acids. This one's kind of not as straightforward, but we do want to see who is the one that is accepting and giving away electrons. So electron donors and electron acceptors. So first thing I'm going to look at here is my HF and my F minus. And I can already see that F minus is the one that would want to get H plus, and therefore has also lost a proton, and therefore this is going to be one that's considered a base. Again, I look then between my other pair here, and I see that this is a proton acceptor, and this was a proton donor, and this is a proton acceptor, and that it accepted a proton to get here, and therefore this is considered my other base, and this is considered an acid. So when I'm looking at which two species are going to be considered bases, I would definitely say that it's going to be water, and it's going to be my fluoride ion there. And that's simply based on who is accepting and donating protons. All right, now this one's a bit trickier because this one's not as straightforward. But I can say with certainty here that when I look here at OH minus, I know that OH minus is going to be a proton acceptor if it wants to get to water. And so therefore I can say that OH minus is definitely a base because it's a proton acceptor for sure. Then when I look at this one, I can see that, oh, this species here definitely gains a proton if it goes across the channel. And so this one is also going to be gaining a proton, and it's a proton acceptor, and therefore that means that it is also going to be considered a base. So basically you're just looking, you're looking at what is going to accept and donate protons in these kinds of equations. And I don't know why the Bronsted-Lowry acid-base definition is so hard, but I would say again, just to cover all your bases, write down all of the definitions, have them next to you at the ready, and make sure that you have maybe some examples or some sort of understanding about what they mean to you to make you memorize them or help memorize them easier. Okay. And then finally, I wanted to touch on this kind of equation again, but with a base just to kind of hone in. So this is a different base. This is KOH, but again, it is still a strong base. Again, anything that has OH in it is definitely considered a strong base. And I say again that it's without changing the volume, and therefore we know that something is significantly getting an increased concentration. And so when I look at the following, I'm going to see that, okay, what is happening to this overall? So I'm increasing the OH minus concentration. So already, if I'm increasing the OH minus concentration, I can cross out C, D, and E because I know that I'm increasing that. And that means that also the pOH is decreasing. Okay, well, that didn't narrow anything down. The other thing I can note, if the concentration of OH minus is increasing, then the concentration of H3O plus is definitely decreasing, and that then narrows it down to E. And also to make like a sanity check, if the H3O plus is decreasing, then the pH should increase, which makes sense because basic solutions are going to have a high pH, aka an increased pH. So I hope that that makes sense to everybody and you all are kind of feeling a bit more confident about Exam 2 stuff. Again, please go check out your Exam 2 study guide overall to make sure that you're happy with everything that's going on. And then I will see you all tomorrow with Exam 3. All right.